Good. So let's talk a bit about our AI. So if you feel excited about at least some aspects of what AI might be able to do for us, raise your hand. If you feel a little bit, at least a little bit scared about at least some things that AI might cause, raise your hand. OK, so raise your hand if you raise your hand both times. So it seems like we're all both excited and scared, quite unanimously, which means it's a great idea to think about how we can get the upside and without, hopefully, the downside, or how we can steer this this development in good directions, which is very much something I personally believe that mechanistic interpretability can help with. So before we go on to Dylan Hansfield Manel, I want to just give you a little bit of personal MIT pep talk. I think it's clear that you're already interested in mechanistic interpretability. Otherwise, you wouldn't be here this morning. But I think there are actually many different reasons why one can be excited about it. They're all good reasons. So let's look at them a little bit. If you do traditional machine learning, you have some data, and you train up an inscrutable black box model that can do some cool stuff, then what can mechanistic interpretability add to this? Well, first of all, you might want to do mechanistic interpretability because you're a curious person. It's just really cool if you have a system doing something complicated to figure out how it works. I personally think of physics, for example, as just being mechanistic interpretability applied to the universe. So how does this thing work? Then you might end up with a slightly better understood model, and you'll have a lot of fun in the process, realizing more about how it works. That's the lowest of the 4 ambition levels I think one can have, and that's already enough to motivate me to want to work on it. The next higher ambition level is maybe we can not just understand a bit more about how our neural networks work, but actually understand them to the point that we can diagnose their trustworthiness to some extent. Maybe we can learn something about whether the LLM thinks it's telling the truth or not, or whether it's being deceptive, or some other aspect of it. So we can at least know, like, is this particular thing something we can really trust, running a nuclear power plant or not, or whatever. If we take it up one more notch in ambition level, and we love being ambitious here at MIT, you could say maybe we can actually do mechanistic interpretability so well that we could even improve the trustworthiness rather than just diagnose it. Figure out how some things in the models can actually be changed based on the insights we get to make it more trustworthy. And finally, for the moonshot, and we love moonshots at MIT also, maybe it might be impossible, maybe not, is what if we can actually guarantee trustworthiness? What if we can actually, maybe with the help of AI itself, figure out ways of extracting out all the relevant knowledge out of the black box and maybe re-implement it in some other kind of architecture which lends itself better to formal verification, so that at least for some systems that are applied to safety critical things, you can actually have a guarantee. This might sound very hopeless. You're not going to tell a grad student to go look at 1 trillion parameters in an LLM and tell you when they're done, right? But we're not alone. We can, of course, use machine learning to help us with these things. And I think it's worth remembering that there is an interesting math fact which is on our side here. It's much, much harder to come up with a proof than to verify it. And I'm not just talking about proofs of mathematical theorems. I'm talking about formal verification also. So if you have some sort of AI system that says, here is the proof that I'm going to do what you want me to do, or I'm not going to do this thing, of course, I'm not going to be able to read a crazy, super, mega long proof. But maybe I can read the proof checker that I really trust, and the proof checker says this is OK. So if this sort of vision would work, it would become a little bit the inverse of how we use virus detectors today. If you have a virus checker on your computer, if it can prove to itself that this software is going to cause harm, it just refuses to run it, blocks it, right? In this super moonshot mode, it would be the opposite. Unless the program can prove to the virus checker that it's actually trustworthy, it won't run it. And maybe there are some kinds of programs that are, because of complicated Gödel reasons or whatever, can never be verified. But maybe the set of all the things that can be verified is still vastly cooler than any tools we have today. So there may be a possibility that we could have really amazing AI that you could actually trust. Not saying this is possible, but I think it's definitely too early to say that it's impossible as well. And I wanted to list this as sort of the moonshot on ambition levels here. And I want to stress that one thing here that I think makes many people I know very gloomy and be like, it's hopeless, we're never going to be able to verify anything because neural networks are just spaghetti and it's too hard to understand, is to remind ourselves that even though many people, especially very young people today, tend to put an equal sign between AI and neural networks is just one particular architecture, of course. And neural networks are currently by far the best game in town for learning knowledge from data, but they're not particularly the best game in time for runtime execution of things. They're a particular massively parallel implementation of computation. We have many others of those too. So if you're actually interested in this idea of having formally verifiable stuff, maybe you still use machine learning to learn the stuff with neural networks, but maybe someone can invent some other architecture which is more easily verifiable, and you can take some of the mechanistically interpretable stuff that you've extracted and recoded in some sort of other way. I wanted to just lay out a little bit all the different reasons why you might be excited about mechanistic interpretability. So we're really pumped when we go into this conference. And if the moonshot could be accomplished, I think that would be really fantastic. Because personally, the only way I would ever trust something which is way, way smarter than all of us is if I can prove it. Because no matter how smart it is, it can't do the impossible. So for a final piece of optimism, let me just say something cheerful about mechanistic interpretability itself. I think there are some good reasons for thinking that this field will actually be able to make very rapid progress. That's why I've had so much fun working on inviting you all to come to this meeting. Why do I think that? Well, let's compare it with regular neuroscience. We are in MIT's neuroscience building here. Neuroscience has made enormous progress in recent years, obviously. And we have some world-class neuroscientists here with us in the conference. You'll hear a panel with some of them this evening. Artificial neuroscience, or mechanistic interpretability, has several advantages over old-fashioned or non-artificial neuroscience. First of all, they have such a hard time, the neuroscientists here in this building, to get IRB approval to even do experiments on human brains in the first place, right? Chris, Ola, have you ever filed an IRB application? Isn't that awesome? You don't need to. And they struggle so hard to make high signal-to-noise measurements from neurons in human brains. If you're lucky, you can do 1,000 at a time with Ed Boyden's multi-electrode arrays that I worked with him on a little bit, and so on. But it's a complete pipe dream for them that you could just read out all the 10 to the 11 neurons all at once from the human brain and just record everything with zero noise. Well, in artificial neuroscience, easy. That's it. We can do that, right? Massive advantage in data access. Another thing that I think a lot of neuroscientists would love to do is just invent their own organisms, like that are much simpler. Let's invent 67 other kind of animals and study them instead. They can't do that. But you can create whatever neural network architectures you want and train them in whatever weird ways you want in a way that regular neuroscientists cannot. And finally, if you look at how many people there are in the world working on traditional neuroscience, there's a lot. We have a whole building for it that you're in, right? How many people are actually doing mechanistic interpretability? Very, very few. But what I think that you're going to see today and tomorrow is that even though so few people have actually worked on mechanistic interpretability for a relatively short time, the progress has been massive. Massive. I challenge you to get through the morning session even without having this feeling that, wow, there's a lot of momentum here. So if so few people have already been able to do so much in mechanistic interpretability, then imagine how much more can be done if more people get into this field, with it being so much easier in these other ways than traditional neuroscience. So let's be ambitious and aim high here, because I really think this field is incredibly promising. It can go incredibly far.